First of all, thanks for having me and for the amazing event. I am Moussab. I am a data scientist, programmer, and German company manufacturing connector and cable for electrical vehicles. So I have conducted my PhD and then supervision from Professor Thomas and Professor Info. In the domain of the field of EAI for quality inspection and detection, so utilizing manual detection for quality inspection. So, good. Can skip this one. So, we go review about my presentation today. So, first of all, we'll go through quickly on the smart manufacturing and manual detection. In smart manufacturing, the manufacturing technique, and look at the state of the art technique. Then we move to, sorry, this is we skip the last one, the manufacturing in cable assembly, then conclusion and future outlook. So, starting with rough overview of the regulation industry, because when we are talking about smart manufacturing and AI manufacturing, we have to grasp the regulations of the industry itself. So, as everyone knows, in the early 1780s, the industry was started and has been evolving since ever until we reach the latest 1970 to the industry 3, where we have seen utilization of computer automation and automated production lines. Then the journey push forward to then we start hearing about industry 4, and when we start using massive data coming from the sensor and devices, networking technology, cyber physical systems, and AI has been introduced to the manufacturing systems. But of course, the journey never stopped, and now recently start here about this 20 about industry 5. And what we see for there, it's really bringing the human back to this loop. So we have seen intensive use of AI and automation in industry, and somehow people want to forget it there. So replacing, automating everything possible process there, getting rid of human forces, and now we start realizing, okay, human can be never lifted out from this process, and start thinking about how to bring this human experience back to this loop of manufacturing. Good. With that, now it's clear also the smart manufacturing. Smart manufacturing is the utilization of state-of-art technology with the data, the massive data, on the shop floor, in order to achieve having a high efficiency, adaptability, and intelligent system. And what is the intelligent system? It's not, we're not talking about AI model, we're not talking about program, we're talking about really an intelligent system. And by setting down the definition for smart manufacturing, we can have a quick look on the can we use AI in manufacturing and smart manufacturing, mostly in predictive maintenance, process optimization, supply chain optimization, and quality inspection, which is the focus of our presentation for today. Now, quickly looking at Rosenberger industry. Rosenberger is a sales and manufacturing company in Germany. We are a huge concern, consists of 15,000 co-workers worldwide, and we are involved in multiple manufacturing processes, from injection molding to prototype assembly and building technology. So, of course, such a company needs to adapt to the adapters for the state-of-art technology, and there is no exception. So we have started and evaluating on how to adapt AI, IoT technologies in our processes. So we have the major 4 areas. One of them is the digital twins and the assisted administration shuttle, the other one is the instance learning analytics, and smart warehousing, and at last but not least, automated for the inspection, which is the focus of today. Good. So, quality inspection. So, of cost, what is the major metric in production, manufacturing production system, and does it start with AI? So it means in the past we have some computational methods for quality control, closing measure, among many, the six analysis, analysis of variation, root cause analysis, the RCA, issue, Carlo system for root cause analysis, multivariate scale process analysis, SPC data, time series analysis, and many among others. But as the production process is getting more and more complex, these conventional and traditional methods came to their limitations. And this limitation leads to a low detection rate and a high true-positive rate or recall rate. What does that mean? For us, we missing defects, wasting for time and resource. Compounding issues is getting bigger and worse when the final products arrive to the customers. So what's the solution? And why is that? So the solution, why is that? The limitation of this conventional traditional methods, it's the limitation for handling the process complexity, as we said. With the specification comes from the customers getting more and more, getting more increased, and this increase in specification, the process and the line process is getting more and more complex. And with the complex is getting, with the process getting complex, the data is getting also complex, beneath it. Therefore, these traditional methods came to their limitations. And it needs a heavy data preparation, feature engineering, so using ANOVA or using SPC analytics. You cannot just feed to the data. It will be a time-consuming task to prepare the data for these methods. Adaptability. We are producing 6,000 different parts, so we don't want to do a solution for every single part. So we need to have, when we have the process, the underlying process initiate a bit, we need to have a quick adaptability for the models to these changes. And we need a kind of near real-time response. We have response and the feedback from any solution as soon as possible. So, knowing another limitation and knowing the aim of the goal, we would like to build a kind of broad model that addresses all these challenges for quality inspection. But as you said, the quality inspection, one of the approach we want through is the animal detection. So we utilize animal detection to identify the kind of eligibility or anomalies in order to inspect the quality of our products and processes. But before that, let's have a quick look on the animals itself. What does that mean, especially in the context of manufacturing and smart manufacturing? So animals is anything different, anything deviate from the normal behaviors. And in the context of smart manufacturing processes, it's referred to any deviation or irregularity in pattern and data pattern that significantly differ from the expected or normal behavior. As we see here, a kind of abnormal behavior and irregularity in the process. And by looking at what talking about process and meaning here is the underlying data we need. This we can define as an anomaly. Now, setting the definition of the anomaly, let's have a look at the types of the anomaly. Why it's important? Because anomalies are not the same. So you could have different types of anomalies. For instance, we have the ground anomaly, which is an anomaly we can have as an outlier, or the anomaly spotted alone, far away from the population. You could have, here you see the top left chart, the scatter plot for the point anomaly and the line plot for the point anomaly. We could see, we have also a kind of collective anomaly, so only one point, more a group of points together, and it's going to be close to each other, so it's also spread over the whole series. As I said, another diagram, which is the most complex one, is the contextual anomaly. So the contextual anomaly, it's a kind of, I have a set of points. When I look at them locally, I see there is no big difference between them. They are always close to each other. But when I look In the global context, I see that there is a big deviation between this group of points and the one process. For more details on that, we have just recently a chapter in the book with Professor Kim talk about innovation in smart manufacturing, where we elaborate more on this type of economy and how to deal with each type of thing. Okay, so now having the smart manufacturing look at animal itself, so let's have a look on the challenges with detection in smart manufacturing. And these challenges can be split into different areas. Some of them coming from the data itself, and other ones coming from the domain. And the third part of the challenges are the data challenges coming from the model itself. So let's start with talking about the data. The data, usually when we talk about smart manufacturing, we're not talking about any time series data or any univariate data. We're talking about high-dimensional, multivariate time series data. We are talking about impedance data because the anomaly itself is too rare and our server-wise. So usually when we talk about the detection in any other fields, we are talking about something, an anomaly ratio of more than 5%, and it's in smart manufacturing, 5% is too much. And therefore you will find something like less than 1%, and this is what we call it very critical impedance data. So anomaly is too rare, but it costs too much. The dynamic evolving and stationary of the data drifting, multi-modality of the data, so the same data is not showing the same pattern all the time, different patterns. The labeling and the ground truth, how to say this is effective part or not, is something, there is no objective criteria to say this is effective or not, this is not 0-1. So this is the ground truth is high, difficult to establish. So now, from data to the domain specific processes, as we say, the complexity of the process, the interdependencies, as we say, we don't look at the process itself, we are looking at the whole process. And so there is a cause for the anomaly having proceeding steps, not on the steps we are looking at it. This kind of interdependency between the process itself, it's giving a characteristic of the data, which we call high-order data. High-order data means this data is high-dimensional, coming from different steps, and there is an interdependency between these steps. And of course, very specific challenges. As last but not least, is the model-specific challenges, which is we need to real-time and near-real-time detection and scalability, similar EAI, so we need an actionable insights, and performance and music selection. Good. Going back now to the aim that was very well to advance our model that does all these kind of changes. Good. So before we talk about our process, we elaborate quickly about different techniques of anomaly detection, the different types of detection stemming from the underlying different ways of learning, which is the supervised learning, in other ways, the well-known one is the supervised approach. So of course, it has high accuracy, predictability, and specificity of the data, but following that, we need labeling. And as we say, we have a problem with labeling the data, establishing the ground truth, and also it's something with the problem. On the other hand, unsupervised learning and supervised learning, we feed the model with unsupervised data and it's the cluster the similarity try to group this data to different groups or clusters. Usually it's two clusters, one is from one is for animal data. For management for label data, flexibility, stability, but it's less specificity, so it's not adaptable for any changes. Similar, it's not similar at all, or difficult, and the cost of dimension, because it's high computational consuming, and it's coming to the high dimensional data, then any kind of unsupervised view of unsupervised algorithm will suffer. The other way is the semi-supervised, the last one, which is a combination of both, which is okay, you training my data on normal data, and then trying to learn the normal behavior of the data as the majority of the normal, and then making the test or making the test on unlabeled data and the validation on the small subset of the labeled data. Good. Now quickly have a look of the state of art perspective when it's come to manufacturing in smart manufacturing, for manufacturing at all. So we will have different materials, it's the type of the anomaly itself, and the type of the dependencies. We split the dependencies into global and local. As I said, we are talking about collective and contextual anomaly. Sorry. So we need to look at the global dependencies. Good, starting with unsupervised. We have seen that before 2013, the major benchmark models were unsupervised models. Okay, we understand this is the heap of the deep learning and unsupervised and semi-supervised approach was not that known at that time. Then moving forward to the unsupervised learning, we see that now was used before and now still used heavily in the latest quantitative training. And semi-supervised is really something new that now you can see it more benchmark models are semi-supervised models. Focusing on USAD is unsupervised anomaly detection model. It's using model-based reconstruction-based model. It's something similar to the approach we had. And here we see that it can address the point anomaly, can address the collective anomaly, but it's not the contextual anomaly because the automated itself can capture the long context of the data. And of course, it can capture, it should be the local, not the global anomaly. Granadine, on the other hand, it's something similar to the USAD, which is utilizing a transformer. Same aspect, but utilizing instead of autoencoder as a transformer, and it can now capture all these three types of the anomalies and also the global context. But it's separate from the local context, so it cannot still capture that. What we call it, this is that subtle anomalies, that fine anomalies hidden within the local context. Again, it's again just to understand network for detection, also addressing something similar to the TRAN, but like general networks, to capture the local anomalies because it's built as an amplifier with this adversarial training approach. So it's amplifying the local anomalies, but it's suffering from the global dependency, the global context. And therefore, making our ideas clear, we need a model that utilizing the power of the transformer and the network itself. Okay, maybe here that's the last one. It's something similar to the transformer, also utilizing the transformer. Again, so what to say from here, we say that we need to utilize the power of the transformer models and the power of the adversarial network, and our approach was to combine both of them together. And we look also on the anomaly detection as a from our perspective. We have seen in the 2023 more and more research around utilizing transformer and less are using lower atom folder or even the LSTM network. Now about the performance, so here we had utilized the Python detections for the dataset benchmark and the benchmark models, and as a metric we have utilized area under the curve, rock, and mean to measure the performance of every single many of these models. And as we see, most of the deep learning and the transformer models, they show a high performance. And if we look here, it's our models, the IRT has achieved the highest performance. Good. Now, before we move to our approach, I'd like also to highlight the idea of choosing the metrics itself, because choosing it's important to develop more model. It's as important of developing a good model is to choose the metrics itself, but also the metrics it can differ from different processes from the scenario to another. And also the metric itself is guiding because of through the development process of the model itself. So utilizing accuracy is not a question here, it's not an option. That's why you see people are using the area under report, influence score, and also not providing influence score, so it's not the definition for scores at the harmonization between the recall and the precision. Now, we have seen in research that we must start to introduce, for instance, the time awareness influence score or the window-based influence score. So just to show that we are not looking on one point in time, we're looking at a window itself in order to capture the whole dependency around this point. And this is the metric we have. That is the influence score of time awareness. Yep. Good. Now it's time to talk about the process itself. So our process is a cable assembly. So it consists of different piece parts. We are assembling different parts together in order to have this final product, which is the cable for the battery and the electric cars. And as you see, we have several machines. In different machines, each making running either in parallel or sequentially in order to have this final product, which is called cable. Good. Now looking on the defects, so you can see that this kind of cover defect, and the brute force is not the modeling process itself, but the brute force, which is stands for bigger than 5,000 Newton, requiring something less than 6,800. Here only highlight, for instance. When it's coming to the brute force, there is no single way, physical way to inspect the product without destroying it. Yeah. So if you apply this more than 4,000 Newton, you are destroying the product, and it's 1% that you are destroying all your product in order to escape the quality for the parts itself. That's why in physical or chemical inspection here is not an option, and you can either need to find out something else to inspect data force is the best way to do it. Data. And of course, the inspection itself is time consuming, costly, and sometimes requiring, for instance, an X-ray machine, which is adding an extra external cost for inspection and having a big impact on the final product. So we're not that competitive anymore. Right. But the process, the model itself consists of two phases. One is the inspection on the product and the data being underlying the process during the product itself, and the offline inspection is then offline inspection where we are utilizing the camera, computer vision models to identify and analyze the defects of the product. Our scope for this and the online inspection model itself. Good. So this is how we see it, and it's just good group of the data. From this kind of process, then here the data came out with a kind of multivariate, because we work on different parameters, the welding mode, the time, the temperature, and it's high order because it consists of different processes, and it's a time series, depending on the time. So this is here the high order multivariate time series that we before. How does it look like? It's like that. What do we see? We see different multivariate, different parameters, evolve over the time, and getting from different steps also. So here we see the steps, and also we have the step of touching, means that could be kind of what we call this sparsity data set, sparsity time series data, or uninterrupted time series. Sometimes you have gathered machine from honey, for instance. Yeah? So this other challenge, another challenge of data. So just to recap, so influencing the preceding steps, scarcity of the anomalies itself, the generalization, explainability, and the high initiative. All this require us to think about a new model and all the state of the art model we could address all these challenges, and that's why this was the main reason to develop our model. And the company supported of this kind of research to bring a new model. Just one last thing to talk about the data characteristic of the data. This is the kind of nucleosity. It's known when it's come to the time series that sometimes the interdependency between the multivariate itself, the different variate of the time series is differing over the time. As we see here, for instance, the correlation between these two parameters are different from here to here. So this is also going to add another challenge to our data. Good. Quick, as we said, we have the transformer, the generative network, and as adversarial learning, and also we use it to classify with the exception as classifier. We can how the phase have short-term, quick, full. Normal data processing and windows, the transformer consists of one encoder and two decoders to boost the performance. One will, the first, they are playing against each other in an adversarial way, and adversarial, as we say, will amplify this kind of fine noise or solid noise, or the small local noise, as we know that software is known for capturing the long distance or the long the global context. The data, but when it's coming to the local and the final is suffering from that. That's why we introduced also attention mechanism, the self-attention, the lower one from the transfer of the global witnesses, and the Gaussian attention to capture this kind of specificity of the data. So that again, to get this kind of amplifier and find if there's any dependency between the point and the repertoire around it. Having these two kind of attentions, then we tune this using another parameter called the theta. And after training the model, the adversarial learning, then we are using the encoder and the second decoder to output the anomaly score. The anomaly score, at the end, it's just a reconstruction vector, and here I want to highlight this vector. It's not a scale. And why is that? Because you could have, if we are looking usually the normal anomaly score, and most of the research they are adopting this kind of looking on a threshold, setting a threshold, and with different statistical models. And kind of a threshold be above the threshold is anomalies below the threshold, then it's fine. But here we are ignoring the direction. So we are looking at this value, the scale value, so we are ignoring the direction here. And that's why we are taking these anomalies as vectors in order to represent the direction and the scale together, and then we're feeding them coming from the different. We have two vectors from the first encoder, decoder, second encoder, decoder, and then accumulating with alpha and beta, alpha and beta equal to 1, and then combine them to one vector and feeding it to the classifier. The classifier is the SVDB, then you have a classifier to set a dynamic threshold. Good. So just here to highlight this, there's two attention mechanism, the self-attention and the Gaussian attention. And this is how we are taking the loss 1 and the loss 2 coming from encoder 1 and encoder 2, tuning them over the alpha and beta, and then using a grid search to find the best threshold, and then having the F1 score. Utilizing the F1 score and distinguish between the normal and anomalous Good. Now to the performance. Quickly here what we see. This is a normal input. As we see here, it's consists of 120, I think 132 different parameters. That's why this is high dimensional multivariate density data. And when we are looking at the tuning, this is the theta. Theta is tuning the attention, the self-attention, and the Gaussian attention, which self-attention is for the global context or global dependencies, and the Gaussian attention for the local dependencies. And we are tuning that, and from here we see that theta between 0.3 and 0.4 gave the best performance. Here it is just the probability loss on the training. This is how the enormous input look like or looks like. And this is just the overall fiction. And now it looks like that. Here what you see is the weaving point, I think, weaving different three parameters, and here you see this the threshold, and by setting a threshold of 0.014, then you are setting, okay, so then we should do this and then we should. Good, it's a little bit of cost. Okay, this is script because it doesn't belong to this, doesn't belong to the first part of the thesis. Good. And now we just a quick comparison between other against the benchmark models. And we clearly see that our model exceeds most of the all of the benchmark models against the three benchmark data sets. By looking on the whole ops, so that we need to productionize it both into the production, so starting the shop floor, collecting the data from different sensors, from different machines, different steps, quality check data, and data. Then we push this to our cloud, which is Microsoft Cloud, in order to clean the data, prepare the data for training, for air training, and you are training the model, and then deploy it back to the edge on the machine. What does it look like? Okay, as you see, this is the automation environment, different levels, from the sensor to the controller, then to the AS system, and then you are bringing this data over the GCP proper, send it to the cloud, to the event hub, and collecting data, making the features, having this feature set or feature store, which is the knowledge of the knowledge base, and then developing the model and deploying it back to the shop floor. Good. So now feature directions. So the model is working. Detection was really highly accepted. And now we are thinking about the next phase, which is the tabular data. As you said, we are focusing on the time series data, it's not the tabular data. So when we are talking about the tabular data, it's more the figure data, for instance. When was the last maintenance, and many, which machine, which tool, material itself. We can introduce multiple data there, but then we are ignoring it when we are focusing on the time series data. Because we know that the transformer is more suited for time kind of time series data or sequence data. That's why by introducing kind of another embedding phase to capture the technical data and this tabular data and embed it to the time series, we have able to use this further more information into our AI detection model. And on that, I will be talking in the Cuộc Summit in the summit of November here in Germany about how to introduce tabular data into the AI model, into the transformer model. Back to the, as we said, the human back to the loop, and really in the last it was more about automating everything, deploying AI everywhere, getting rid of the people. Now we have started to realize that people actually need to have kind of interactive model. It's not about a model that exists by itself, and either it's not consistent that the model is assisting the people. It's both. It's model assisting the expert and the expert are assessing the model, but on that in an interactive way. And now with this type of the generative AI model, we are working on developing an AI agent that making the same thing, more focusing on the computer vision, and it's making an interactive dialogue with the expert. So the expert can even ask why you have made this decision here, for instance. What is the decision itself? They can give you the feedback will allow the model can tune. Here are talking about tuning, but tuning the model with the new knowledge. So I is also talking about this topic in summit in Munich in the 14th and 15th of November. Good. Now, to dissertations out of these pieces we have published. Paper in the Journal of Manufacturing System, it's accepted, will be published soon. And a chapter in the book, in collaboration with Professor King Fu. In the Spring of Natural Studies Environment, and it's now available and accepted and available. With that, I'm done, and I hope that you have some questions for me. Thank you.
Thank you, Moussab. So we have maybe some questions. Thank you for the presentation. I have two questions, please. Firstly, on your Rosenberg data set, can you say us about the distribution between data for anomalies and with data for normality? Because I think that
actually it's
yes. So my first question, perhaps you can answer this question first.
So this is actually we are plotting the distribution between the normal and abnormal population of samples. It's really hidden within it. So I can quickly maybe find something to share that show this kind of hidden anomalies, and we could define or some element that anomaly. So it's really hidden within the population. So there is nothing. No, out of the box, outside detection can isolate this kind of hidden anomaly. Let me just quickly have a lot of slides for this. Now this is my phone, so not that.
If you have 80% of data for normality and 20% of...
No, distribution is less than 1%. I said that. It's anomaly ratio is less than 1%.
Excuse me?
The anomaly ratio is less than 1%.
Less than 1%, okay. So that's why you propose an assessment of abnormality score. So my second list of questions is, how do you justify this assessment of anomaly score with two variables, alpha and beta?
So the alpha and beta is for one is, as I said, it's coming one from this is the adversarial element. So the alpha is more for the adversarial score, and the beta is for the normal score. As we said, the alpha and beta is coming from encoder. Encoder 1, encoder 2 are playing against each other in an adversarial way, and that's when I get the reconstruction vector from the first encoder. Because one encoder first encoder, then I have this loss, and encoder 2. It's the second loss, and then I have to tune them, because I know that one of them is coming from the adversarial loss, and the other one is the normal loss. So I have to go back here quickly.
Okay, so can you go back to the slide 29, please? Because regarding the answer, I do not understand if this score can be interpreted in terms of amplitude of the anomalies or a gap regarding normality. I didn't understand that. 29.
29.
You gave an example, very interesting, but the interpretation for me is confusing. Not 29.
This one?
Yes, this one. So, what in red color, It's
Yeah.
what you identify as anomaly, correct?
Left side or right side? This one or this one? Which chart? This
On
or
the
this?
right, yes, on the right, yes.
Right, okay. Okay.
So here there is two anomalies, that's correct?
Yeah, that's it. Yeah.
It's correct?
Yeah, there are
So
two
there is
elements.
another gap at the extreme right, so why did you not jump this an anomaly here? Oh, the last one, yes.
First of all, there are three, there are four. So this window is involving this one, this
Okay.
window is involving these two,
Yeah, it's clear.
and this one is ignored. Yeah? So it's not depending on against the tuning of the SVD itself. So maybe here there is the from the amplitude it's the same, but from the direction is not that
So
different. And this the amplitude of the anomalies here is
yeah,
is ignored.
and this
But again, what I would say here, this is the output of the SVD itself, so means that the amplitude and the direction is only considered.
yeah. So can you explain me again in parallel? It's a second anomaly. On the left there is another gap, but for you it's not an anomaly. The same amplitude pattern. So you see, at the second identified anomaly. Here, yes. On the left, there is another one. Just on the left. No. Just on the left. Here, yes.
This
So
one.
for you, it's not
Ah, this
anomaly.
Now this both are anomalies. This window here, you see this window is covering both.
It's the same.
It's a window has two anomalies.
Okay, thank you. Excuse me.
So maybe here this is the one you need to be a bit adjusted. But this is a window covering both.
Okay, thank you. Another question?
Hi, Chef. Thanks for your presentation. I just asked you about the technologies you consider in the end of your topic. You talking about the 10 AIs, and I see all AIs. But as I know, the all AIs is for improve the large language models. And I see your topic about the image processing and for the anomalies detection. So how is useful and is the generative AI useful in the manufacturing? Why you mentioned about it?
Good, exactly. So generative AI it's characterized for two things. First part generating, taking the generative bar and the interactive bar. So generative bar, let's talk about the generative bar first. The generative bar is generate something. Because it's at the other end, generative AI, it's not large language models. Generative AI is bigger than only large language models. Large language models are specific to generative AI. And that's when we talk about GPT, for instance. G is generative, B trained, T is transformer. So generative AI is bigger than large language models. So generative AI will generate something for you. With this concept of, okay, I'm training on my good data, and I'm asking him to generate for an input and output that was handled, and then measuring this kind of difference between the input and the output. This is the generative way, and this is how GAN, for instance, GAN is working. So now this is the part to generate. Part again to the large language model is the interactive way. So now I can ask my model, for instance, why it did make this decision. And he can answer me, for instance, I made this is a defective bar because you can see a defect in the upper left bar, which is small defect or small scratch. Here it's more for the computer, when it's coming to the computer vision. So you can use generative vision AI model to generate an image for you, the rendering of this image or representation of this image, and then comparing to the original grayscale or character image, and finding out the differences between them and highlighting the defects. So this is the idea of generalizing generative, and also large language for more interpretation and interactive between. So now our operator will ask the model why and where is the defect, for instance. And if also can ask, say, I don't consider this as a defect because of that and that and that, and automatically this will be a loop of feedback to update the knowledge base, which we call the knowledge base of the LLM models. So this, we need to see generative AI as generative, to generate something trained on only good data, and the large language model is for interactive dialogue between the operators and the model.
Okay, thanks. About you talk about a loop back, right? So
Yeah.
in the loop back, how do you think you the human feedback is
When you have this human who will ask the model or investigate on the performance of the model and even tune the performance of the model, tuning here means it's really to update the knowledge base of the model itself. Having an opinion from the expert saying, no, this is wrong, I see this as a good part, and with justification, this is what you call the evidence, and with that, I'm taking this as a loop back, and this is an online loop back, by the way, and we go back to the model and tune its knowledge base. You can search for something called RAG, OmniRAG. It's something new have been introduced from Microsoft in the last 2 months. It's called OmniRAG for generative AI.
Okay, thanks for your detailed explanation.
You're welcome.
Thank you. Another question? So just maybe one question, Moussab, you can answer in one word. In your work, what is the most challenging issue in terms of responsible AI?
It's this dataization. Who has the model of the AI? The model or the human? And we need to keep the responsibility for the human, not for the AI. For the authority for the AI. So.
Okay. Thank you. Thank you, Moussab.
Thank you for having me. Very good.